Welcome back to The Explainer. Today, we are stepping out of the textbook and right into the physical world. If you want to absolutely crush your physics exams, you need more than just theories. You're going to have to think like a detective of the natural world, stepping into the lab to uncover the fundamental truths of the universe. And to do that, you need a rock-solid methodology. You need the investigator's toolkit.
Okay, so let's dive into the core question here. How exactly do we prove the laws of physics without getting burned, shocked, or, just thoroughly confused? Physics is all about precision and safety. It's really not just about blindly following instructions on a worksheet, it's about understanding the why behind every single action you take at the lab bench. We are trying to find true values in a completely chaotic world, and to pull that off, we need a flawless system.
So here is our roadmap for today. The 6 steps to experimental mastery. First, lab safety essentials. Second, choosing the right tools. Third, precision, accuracy, and errors. Fourth, processing experimental data. Fifth, the power of graphs. And finally, number 6, planning and evaluating investigations.
Let's jump straight into step 1, lab safety essentials. This is all about mastering your physical environment before you even touch a piece of equipment.
Right, so here are your physics lab non-negotiables. I know these might sound like common sense, but these are the principles that actually protect you from real-world hazards. First off, always wear shoes. If a heavy weight slips, your feet literally need that protection. When you're dealing with electricity, always set the power to a low output before turning it on, and make sure to switch the power off between readings. Large currents can cause severe burns, nasty electric shocks, and completely fry those sensitive, expensive meters. Naturally, keep your electrical circuits far, far away from water, taps, or sinks. If you are handling toxic materials, like the mercury in some older thermometers, do it with extreme caution so it doesn't roll off the bench and break. And finally, tie back long hair so it doesn't catch in a Bunsen flame. Bottom line, safety is absolutely your first priority as an investigator. And hey, before we continue, subscribe to our YouTube channel Ace the Exams at acexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, moving on to step 2, choosing the right tools for precise data collection. When you need to measure mass, say in kilograms or grams, a digital top pan balance is going to give you a direct reading instantly. But what you really need to know as an investigator is its precision. This device is typically precise to the size of the smallest mass it can actually register on its current setting, which is usually down to 1 gram or even an incredibly tight 0.1 grams. That precision right there, that is the absolute foundation of your data. But look, having the right tool means literally nothing if you read it wrong. Which brings us to the dreaded parallax error. Whether you are using a simple meter ruler, an analog voltmeter, or a measuring cylinder, your visual alignment is absolutely critical. If your eye isn't positioned directly above the mark on a ruler, the actual thickness of the ruler itself is going to cause a false reading. And if you're measuring liquid volume, your eye must be exactly level with the bottom of the curved liquid surface, the meniscus. Master this visual technique, and your accuracy will absolutely skyrocket.
Now, for extracting electrical data, a digital multimeter is your best friend. It allows you to select different ranges, giving you a measurement precise to the very last figure on its display. But you've got to remember the golden rules of electrical tools. An ammeter measures current, right? So it must be placed in series with the device, meaning it needs a very low resistance so it doesn't accidentally change the current you're trying to measure. A voltmeter, on the other hand, measures potential difference and goes in parallel. It requires a high resistance so it doesn't divert current away from the main circuit. Oh, and always start with the largest range selected to avoid damaging the meter.
Okay, step 3, precision, accuracy, and errors. This is where we figure out how to find the true value amidst all the noise. First up, let's talk about significant figures. This is a definition you absolutely must internalize, especially for exams. Significant figures indicate how accurate we genuinely think our value is based entirely on the apparatus we used. So here is the golden rule. Your calculated answers should never, ever pretend to have more digits than the least precise measurement used in your experiment. If your calculator spits out something crazy like 1.23578, but your original measurements only had 2 significant figures, you must round that answer to 1.2. Seriously, don't let your calculator trick you into claiming impossible accuracy.
So in the lab, you are basically facing 2 types of enemies, random errors and systematic errors. Random errors result in a scatter of varying results. Think of them like shaky hands. Maybe your reaction time on a stopwatch fluctuated a bit, or a sudden draft in the room changed the temperature slightly. Systematic errors, though, are completely different. They are consistent measurement offsets. Think of this like a misaligned targeting system. For example, using a ruler that has a blank space before the 0 mark or an ammeter that reads 2 milliamps when absolutely zero current is flowing. You have to check for these zero errors before you begin, or literally every single piece of data you collect will be systematically offset. And speaking of staying on target, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, back to it. Step 4. Processing experimental data. Let's crunch some numbers.
Take a look at this pendulum experiment. Notice how the investigator didn't just measure the length once and call it a day. They took a first length, then a second length, and then calculated the mean. Taking repeat measurements and finding the mean like this directly helps average out those pesky random errors we were just talking about, which drastically reduces the overall uncertainty in your final measurement. It's a total game changer.
Now, when it's time to actually use equations to process that data, please remember this quote. Do not substitute numerical values until you have obtained the expression that gives the answer in symbols. This is a massive rule, folks. Let's say you're using the equation f equals kx and you need to solve for x. Do the algebra first. Rearrange it to x equals f divided by k before you plug in a single number. Building this simple habit prevents absolute arithmetic nightmares and completely eliminates copying errors.
Step 5. The power of graphs. This is where we visualize the relationships we found.
Here are your rules for graphing truth. Always plot the dependent variable on the y-axis and the independent variable on the x-axis, unless your instructions specifically tell you otherwise. You're going to need at least 6 data points stretched out over as large a range as possible. Then, you draw the line or curve of best fit. This line should be drawn so the points are equally distributed around it. This naturally takes those unavoidable random errors into account. And this next part is absolutely crucial. Do not force the line through the origin, 0, 0. If your best fit line naturally passes perfectly through the origin, congratulations, you've just proven direct proportionality. But if it doesn't, you simply have a linear relationship with a y-intercept. Let the data speak for itself. Finally, step 6. Planning and evaluating investigations. This is the true scientific method in action. At the absolute core of any experimental design is understanding your variables. The independent variable is the one specific condition you intentionally change. The dependent variable is the resulting variable that you actually measure. But here is the real secret to a perfect experiment. All other variables must be kept absolutely constant. These are your control variables. For instance, if you want to see how the mass of a pendulum bob affects its swing time, you can only change the mass. The length of the string, the angle of the drop, everything else must be frozen in place. You have to change one variable at a time, ruthlessly.
You know, the true mark of a top-tier investigator is how well they evaluate their own flaws at the end of the process. First, you need to identify your sources of error. Was it simply impossible to stop heat energy from escaping into the room? Say so. Was your manual reaction time with a stopwatch just way too slow for the rapid event you were timing? Note it down. Second, spot your unmanaged variables. Did the wire heat up and change its resistance when it was supposed to stay constant? Finally, suggest modifications. Could you maybe use an automatic light gate timer next time instead of a manual stopwatch? Could you insulate the beaker? Proposing these specific improvements proves to the examiner that you truly understand the scientific method. And that brings us to the end of our journey through the lab. We've conquered safety, selected our precise tools, battled those sneaky systematic errors, crunched our data, visualized the truth in our graphs, and critically evaluated our own methods. Students who implement these exact physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Now that you have the complete investigator's toolkit, what laws of the physical universe will you uncover next? The lab is yours. See you in the next explainer.